Hello everyone, this is Muhammad Shatan, Assistant Professor of Mechanical Engineering at Abu Dhabi University, United Arab Emirates. I obtained the Master and PhD in Mechanical Engineering from New Mexico State University in the United States, 2016 and 17. This is my talk about the topological metamaterials with non-reciprocal elasticity. This title contains 3 keywords that I'm going to go over them through this presentation: topology, metamaterials, and non-reciprocal elasticity. So this is the outline of this presentation. I'm just going to start with a little bit introduction or overview about my research. Then I'm going to show what is metamaterials, topological mechanics, micromorphic mechanics, and their use for the topology investigations. Also, I'm going to show some of our new results about the topological mechanics of metamaterials. Then I'm going to introduce a new concept that I named non-reciprocal elasticity. Then I'm going to end up with some summary and conclusions. This talk is part of my research on the mechanics of advanced materials and advanced manufacturing. The mission of this research is to mechanics-based design advanced materials, mechanical systems, and manufacturing methods for the commercial and public benefits. This research bridges the gap between the basic science and applied science, like material science and applied materials, mechanics and applied mechanics, physics and applied physics, with the objective of providing standardized methods of engineering and tailoring new materials, new mechanical systems, and their manufacturing methods that would be used for optimizing the performance of some of the existing engineering applications. This is an overview of my research. These are the different research projects that I'm running these days. I do have some research related to the mechanics of nanomaterials and multi-scale materials, also the mechanics of additive manufacturing, the mechanics of nano-confined fluids, in addition to the design and development of micro-nano mechanical systems. Today's talk is related to my research on metamaterials. We are developing new metamaterials with exceptional mechanical properties, especially the mechanical properties. So that's why the tone of today's talk, it is more related to the mechanical applications. Also, I'm investigating on their topological mechanics. Alright, so what is a metamaterial? Metamaterial is an artificial material, man-made material with a microstructure that is specially designed or tailored and engineered to achieve some exceptional properties. What we knew from material science, for example, that all the material properties are related to the material structure. For example, as we tailor the material structure, tailor the material microstructure, these changes are somehow reflected over the material properties. So once we realized this, we came up with the idea of the metamaterial. How about if we're gonna make our own design of the material structure or the material microstructure that could achieve some properties that we have never observed by natural material? So this is the basic idea of metamaterial. And we foresee actually if we try to bring this technology or this concept of metamaterial into mechanical applications, this would be interesting. We can achieve some exceptional mechanical properties that we have never observed before. Like, for example, the auxeric metamaterial. These materials are with negative Poisson's ratio. This is, for example, our design of a 3D hinged metamaterial. This is the unit cell of the metamaterial that is made of a hybrid pi material. And this type of metamaterial has achieved a giant Poisson's ratio of -16. This work is published in scientific reports. So this is an example of a metamaterial with a negative stiffness. This is a composite metamaterial that has shown some exceptional dynamical performance that indicated that this material has an effective negative mass. These are 2 examples of active metamaterial. An active material, this is the one that it changes or tailor its properties in space and time with the aim, for example, of breaking the time reversal symmetry. So like these 2 types or examples of metamaterial, like this non-reciprocal robotic metamaterial that has demonstrated some dynamic non-reciprocity, that this material contains rotors inside its microstructure to break the time reversal symmetry. Also, this is another example of a gyroscopic metamaterial that is a lattice with embedded gyroscopes. There are more that we are expecting from these metamaterials, especially if we can understand their topological mechanics. So what is a topology? From the mathematical point of view, mathematically speaking, topology is the study of shapes. Topology, it is concerned with the properties of an object which are preserved by the continuous change of the shape of this object. In topology, for example, we don't mind the shape as much as we mind the invariant properties of the object as it continuously deforms or change its shape. For example, topology is different than geometry. In geometry is another branch of mathematics. In geometry, for example, the mag is a mag, the donut is a donut. These are two different shapes. They are geometrically different. But from the topology perspective or topology point of view, they are topologically equivalent. They are equivalent topologies. From the topological point of view, there is no difference between the donut or this mug because they are sharing some topological properties. So within the mug or the donut, there is a specific property that is preserved as one tries to morph and it changes its shape to the other one. Like morphing the donut to the mug or the mug to the donut, there is a property. This property as shown here is the gap. This gap is preserved. It is topologically protected. Thanks to this gap, since it is topologically protected, we're going to say that these two objects are topologically equivalent. So they are the same from the topological point of view. However, the tripod knot and the simple loop pose are topologically distinct. For example, if we try to morph the tripod knot to the simple loop, we have to cut the wire. Cutting the wire, it means that we are vanishing the gap. The gap is not there. There is no gap anymore. The gap is cancelled. It means that the gap, which is a property, topological property of these two objects, it is not topologically protected anymore. It is not preserved as we try to morph one to the other one. So this indicates that they are topologically distinct. So in general, we can say that any two topologies, if we try to morph one to the other, or change or deform one to the other, without closing the gap, this indicates that they are topologically equivalent, but any two topologies, if we try to morph one to the other, this required closing the gap or cancelling the gap. This means that they are topologically distinct. So what is the benefit of these topological things? In addition to the things that we knew about the benefits of topology, like making quantum computers, I'd like to bring very interesting example here of as a benefit of this topology. So let us assume that this mug represents a complex physical system that we have been struggling in making or achieving it, while on the other side, the donut represents a simple physical system that we already making it. So in terms of physics, these two systems are two different physical systems, totally distinct. But in terms of topology, they are equivalent. They are topologically equivalent. So what does it mean? It means that there should be one property or more that is common between them. And this property, it is preserved as we try to change one to the other. And this is very interesting. So we are struggling of making this complex system. So if we could able to allocate or define this common property, which is preserved in both of them, that make them topologically equivalent. So simply we can replace this complex physical system with the simple one, and we use the symbol instead. So this means that the donut is finite enough and that we can use it instead of this complicated mark thing as long as they are topologically equivalent. So in general, we can say if we can mind the topology, we can replace complex physical system with the simplest equivalent ones. And in that case, we can make it. Anything that is difficult, we can make it based if we can mind this topological thing. So this is a good thing of topology. In fact, in addition, topology has resulted to the invention of the topological insulator. Topological insulator is a material that is insulating in the bulk, but always has a conducting boundary or a surface. Always here means that this property is preserved. This boundary, this conducting boundary or surface, it is preserved property of these topological insulators. It is topologically protected property. It means that the conducting boundary of a topological insulator, it is topologically invariant that cannot change as long as the material remains insulating. The difference between topological insulator and the trivial insulator is the formation of this boundary, of this topologically protected property. For example, as shown in the animation here, the trivial insulator has no boundary, has no conducting boundary or surface. So, but on the other side, the topological insulator has a boundary that is going to form, as shown here in this animation. This boundary is topologically protected, and this is why we got the name as topological insulator. And as the trival insulator tried to morph or change to the topological insulator, this requires closing the gap. This indicates that the trival insulator and the topological insulator both are topologically distinct, because there should be a transition state that requires closing the gap so we can transfer one to the other or transform one to the other. So the question now, after the success of this topology in realizing physical systems, can we bring it to realize mechanical system with topologically protected properties? Yes, we can. But this requires using special materials like metamaterials. And in the meanwhile, we should understand their topological mechanics or mine their topology. So for this, metamaterials these days is highly recommended. For example, mechanical metamaterials are being made that can host topologically protected zero modes at their boundaries. So in general, we can say that metamaterial can be used for making advanced mechanical system with topologically protected properties. But in the meanwhile, as I mentioned, this requires topological mechanics. Topological mechanics is a perfect tool that can bridge the gap between the quantum and Newtonian physics and mechanics. We can use it to reveal the analogies of mechanical metamaterial with the quantum matter or the quantum or topological quantum insulators, for example. Also, we can use it to reveal some of the properties which are topologically protected of these metamaterial, and then we can bring it to realize advanced mechanical systems. And this is actually what I'm trying to do in my research. There are different approaches of studying the topological mechanics of metamaterials. As of myself, I'm using the continuum mechanics. Why the continuum mechanics? Because from the engineering point of view or perspective, it is more practical than any other approach. So I'm mainly depending on the continuum mechanics, but we do have the classical continuum mechanics. Unfortunately, it cannot be used to reveal these topological things or properties of metamaterial. Why? Because in the context of the continuum the classical mechanics, the material is a composition of points. A point, it has only one mode, one type of mode that it can only move inside the material microstructure. This makes the material, it is acoustic and it is represented by only one mode. So there is no coupling here. Topology requires coupling between different fields, like modes. For example, in the quantum topological insulator, we should achieve coupling between the electrons and magnetic fields so we can achieve some topological behavior or performance of this insulator. The same thing if we decided to use a passive metamaterial, we have to design this metamaterial, its microstructure, that promote the coupling between different fields inside the material microstructure that would achieve some properties which are topologically preserved or topologically protected. And this in the meanwhile require a more advanced model in order to model this material or design this metamaterial, like the micromorphic mechanics. This is what I'm using in this research. In micromorphic mechanics, for example, the material is a composition of particles, and each one of these particles is represented as a volume element that can exhibit three different types of modes, like displacement, rotation, and strain inside the material microstructure. So with the coupling between these three different modes, we can achieve some topological properties using this metamaterial. And this is what I'm using in my research on investigating the mechanics of metamaterial. I'm using the micromorphic mechanics. So these are our results on the topological mechanics of metamaterials based on the micromorphic mechanics. We developed a general model of metamaterial a general micromorphic model of metamaterial. Then we defined a material parameter, which is beta, this beta, that depended on the geometry, the material properties of the microstructure of the metamaterial. We found that depending on the material microstructure, this beta would be zero, positive, or negative. So this defines three scenarios, three states of the metamaterial, which are shown here in these figures. And then we studied the topological properties of these three states of the metamaterial that depended on beta, as I mentioned, would be zero, positive, or negative. Material state, or the case beta equals zero, the acoustic and the optical modes are distinct, as shown as it can be seen here from the eigenmodes representation over the complex plane in this beta equals zero. This is the acoustic mode and this is the optic mode. The acoustic mode is located on the right side of this complex plane, while the optic mode is located over the left side of the complex plane. So both are totally distinct. Another thing that at zero, which when Q equals pi or negative pi, the real and the imaginary parts of these eigenmodes are zeros. This indicates that there should be a localization that is happening here as shown here in this dispersion curve. Like this localization indicates that if we consider, for example, any two particles or unit cell inside the metamaterial, the vibration energy, it is confined at only one of these two particles or unit cell. It is not distributed as the other scenarios or other cases. No, when Q equals pi or negative pi, there should be a localization happening here, and there should be a confinement of the vibration energy at only one atom or one particle of the metamaterial or one unit cell. Okay, and again, these are two distinct modes as shown here. This is for the case beta equals 0. Because of this localization, and because the acoustic and optic modes, they are localized and identical. When Q and pi equal 0, there is no gap is forming. So there is no insulating state for this material, or this metamaterial. It is a conductor. It is not an insulator. It is a conducting material. And in that case, there is no gap is formed. This is for beta equals 0. But for beta is bigger than 0, the positive case, there is a gap is formed. But still, the acoustic and optic modes are distinct. And there is no localization. The localization is not happening in that case. And that's why we're already ending up with a gap. There is a gap is going to form in that case. But still, the acoustic and optic modes are two distinct modes as already shown in this eigenmode. On the other hand, for the case that beta is less than 0, a gap is formed like the previous case, but the difference here that both the acoustic and optic bands went about the origin of the complex plane once. This winding indicates that these two bands had been inverted. This band inversion is known as band twisting, and the corresponding value of the winding number, it is 1. This winding number indicates that there is an existing topology within this type of metamaterial. The band twisting is a property of topological insulator, and this is the reason behind the existence of conducting surfaces of topological insulator. The topological consideration here, it indicated that this band twisting, it is a topologically protected or preserved property of this metamaterial. Like, for example, this band twisting, it is preserved as long as beta is negative for any negative value of beta. This indicated that metamaterial with microstructure of the characteristic parameter beta is negative or mechanical topological insulator. This is very interesting because now we can make passive metamaterial that can emulate the topological quantum insulators. Like, for example, for the case beta is positive, this gives a trivial insulator. Mechanical insulator, yes, but it is a trivial insulator. The same thing for beta is negative. We're going to end up with a topological insulator emulating the quantum topological insulator, but for mechanical application. Last thing that I'd like to share with you today is non-reciprocal elasticity. This is a new concept that I'm introducing to realize effective non-reciprocity in mechanical systems. Reciprocity, it was like a fundamental property of all physical and engineering systems. But now, thanks to this metamaterial, with the aid of metamaterial, we can achieve non-reciprocity and realize some non-reciprocal engineering system or physical systems. Non-reciprocity in mechanical system requires two things, one of two things, either to break the time reversal symmetry or to break the material deformation symmetry. These are the two options. But this should be done, and this is a critical condition, should be done under the same kinematical and kinetic condition. Thus, when we try to test the ability of any system or material to break one of these two symmetries, this should be examined under the same when testing the system or the material under the same kinematical and kinetic conditions. Mechanical systems that achieved non-reciprocity by breaking the time reversal symmetry mainly depended on active materials, like robotic and gyroscopic materials that I just explained or presented. The non-reciprocity achieved by this active material is by definition, it is dynamic non-reciprocity. And this active material cannot achieve any static non-reciprocity. Static non-reciprocity requires a passive material that is capable of breaking the material deformation symmetry, but remember, this should be done under the same kinetical condition. So the question now is, which passive material that can be used for realizing static non-reciprocity? By virtue of the Maxwell-Berry reciprocal theorem, nonlinear material have been suggested to achieve some non-reciprocity. However, this is not necessary. A nonlinear material, it may or may not achieve non-reciprocity, especially static non-reciprocity. This has been demonstrated recently by some scholars. To demonstrate this further, actually, let us compare here the Maxwell-Berry reciprocal theorem with the non-reciprocal elasticity concept that we are presenting here. So as it is known, the reciprocal theorem is used to examine the linearity of the material, whatever would have a linear or nonlinear material. Thus, a nonlinear material is the one that disobeys the reciprocal theorem. However, this theorem requires testing the material under two different kinetical conditions. Like, for example, we have to test the material under two different forces. Under the same force, the theorem breaks down or fails, or at least we can use this test or this theorem to distinguish whatever the material is linear or nonlinear, unless we load the material with two different forces or two different kinetical conditions. This means that under the same conditions, there is no difference between linear or nonlinear material according to the Maxwell-Berry reciprocal theorem. This also means that the nonlinearity is not the trigger to achieve non-reciprocity. It should be something else. It is not the nonlinearity. We found that non-reciprocal elasticity is the essential and the required trigger for a non-reciprocity using a passive material. As shown here in these two figures, a reciprocal elastic material has a symmetric deformation under the same stress amplitude. However, a non-reciprocal elastic material is the one that breaks this symmetry and gives two different strains or two different deformations when it is examined under the same magnitude of stress or stress magnitude. We designed the metamaterial, which is not shown here, and these are the experimental results. This material has been tested under tension and compression, and these are the stress strain curves in the elastic zone that we obtained. Some samples exhibited some linear non-reciprocity, like this material sample, and some others showed some nonlinearity or nonlinear non-reciprocity. This indicates actually that the nonlinearity is not the trigger for static non-reciprocity, but it is the material itself being non-reciprocal elastic, because in this material sample, this is the reciprocal elastic material. We end up with, under the tension and compression, with the exact same stress strain curve, indicating that we do have reciprocity. We don't have any non-reciprocity. We do have symmetric deformation, but for the other material samples, we end up with different stress strain curve, indicating that these materials are non-reciprocal elastic materials. Then I use this metamaterial in monoatomic and diatomic lattices, like the diatomic lattice shown here. Thus, the conventional springs of these lattices have been replaced with the newly developed metamaterial, with this new metamaterial, and these two lattices showed static non-reciprocity when it tested under static loads. Also, I investigated the topological mechanics of these lattices, and I found some interesting results as shown here in these two dispersion curves, in addition to the eigenmode representations over the complex plane. Like, for example, the diatomic lattice shown here. Because of the non-reciprocal elasticity of the metamaterial that replaced these springs, the stiffness and hence the eigenmodes, the stiffness and the eigenmodes of the lattice, when it vibrates to the right, will obtain different when it vibrates to the left. And this results in two configurations which are shown here. Like in this configuration, all atoms are vibrating or moving to the right. In the configuration B, all atoms moving to the left. So when we identified the eigenvalues and the stiffness for this configuration, it was totally different than this one. So, and then we defined an epsilon, this epsilon parameter that depended on the material microstructure of the metamaterial itself. We defined epsilon as a non-reciprocal elasticity measure depending on the material microstructure of the metamaterial. And for the two configurations, configuration A and B, for configuration A, epsilon was calculated positive depending on the microstructure of the metamaterial, while it was negative for configuration B. When epsilon equals 0, which in this case, which is shown here in the middle, the metamaterial is reciprocal elastic and exhibited symmetric deformations, while for the other cases it represented some topological features and performance, and the topological consideration of these two configurations indicated some interesting results and conclusions. Like the metamaterial is topologically distinct under the two configurations A and B. As shown here, for configuration A, the acoustic band that is non-localized, while the optic band that is localized. And then for the configuration B, the two bands, they switch roles. The acoustic becomes localized while the optic becomes non-localized. So this indicates that they are two distinct topologies. And this also can be further demonstrated by observing the transformation from configuration B to configuration A. This requires closing the gap as shown here in this transition state in the middle. And the closing of the gap is happening under only one condition, that there should be a reciprocal elasticity is achieved. So there is non-reciprocal elasticity here, there is another non-reciprocal elasticity here, and which are represent two different topologies, and the transition between them require closing the gap and achieving reciprocal elasticity. So these observations indicate that the trigger of the non-reciprocity in static material or in static systems using passive metamaterial is a non-reciprocal elasticity. So in summary, metamaterials have the potential of making advanced topological mechanical systems. By means of micromorphic mechanics and topological mechanics, I showed the analogies of mechanical metamaterial with the topological quantum insulators. I showed that by tailoring the material microstructure of a passive metamaterial, we can achieve whatever trivial mechanical insulator or topological mechanical insulator. Also, I introduced a new concept, non-reciprocal elasticity, which is required to achieve static non-reciprocity. By means of topological mechanics, I demonstrated that the trigger of the non-reciprocity of passive metamaterial is a non-reciprocal elasticity. At the end, I'd like to mention that we still expect a lot of metamaterial, especially in mechanical applications, and their topologies in the near future. And then thank you so much for watching.